Welcome to Advanced Reverse Engineering. Homework. The homework is to go and find main in user bin cat. Use the information from some prior lectures where we talked about how main gets invoked to go and find the address of it and then produce a disassembly of the first 256 bytes of main and then turn that in. Go look for where libc start main is called. Here's how you can disassemble the first 256 bytes at a given address. There you go. Let's talk a little bit about sandboxing of code. So there are some tools out there to sandbox code for execution. Shade, Sandboxy, still around. But maybe you don't want your code sandboxed. Maybe you are a malware author and you would prefer people not figure out what you're doing. Maybe you have intellectual property in there, right? Maybe your code is code that runs on a gaming console and contains a encryption key to talk to the server. You don't want people cheating. So in those cases, you might not want your code sandboxed. So let's talk a little bit about ways in which sandboxing works. So I promised you a discussion of the trap flag, and so now we're going to get to that. The trap flag lives in the flags register, so you can see here's carry, parity. The adjust flag is still there for some reason. The zero flag, the sign flag, and the trap flag right here. So the trap flag causes the processor to have an interrupt after a single instruction executes. It's basically a single stepping mode for the processor. If I set the trap flag and then I jump to an instruction, that instruction will execute, and then the processor will immediately halt and call my signal handler with a sig trap. And you can go and read about this call if you want. It's not the easiest thing in the world to set up, but you can figure it out. I promise. You all are smart enough to figure this out. If you're super motivated to try to create a thing to single step a program, you'll get there. It's a little bit tricky. How do you set the trap flag? It's pretty easy. The way in which it does it is you push there's no instruction that's set trap, and there's no instruction that's clear trap. So how do you do that? Well, this is how it works. You go ahead and push the flags onto the stack. You then explicitly OR that bit with a 1. Now the trap flag is set, and then you pop it back into the flags register. So this is the thing at the top of the stack. Same thing for clearing it. But wait, you may say, what about if I set it, then I'm going to execute that instruction and halt? Not quite exactly the way that it works. You'll have to jump to the instruction, and then you'll get your single step. There you go. Trap flag. You can here's some code that I think is kind of funny. This body of code right here, not the stuff around it, but this little piece of code comes from a piece of malware. And the piece of malware wants to check to see if the trap flag is set. And it doesn't want you to know it's checking to see if the trap flag is set. So it tries to evade pattern matchers. So there are patterns that we can look for people doing this kind of stuff, right? If you see this, we know you're checking the trap flag. But this does the same thing. It just does it in a weird way. And I think, as a piece of malware, it's sort of fun to go through it and see what it does. The first thing it does is what you would normally do. You push the flags on the stack. That's how you're going to get them. The other way to get them is you can move the flags into the A register, but I think you only get like the low byte, in which case you won't get the trap flag. There you go. So once we've done this, the flags register contains all the flags, including whatever the trap flag is set to. And the top of the stack also contains all the flag bits. So now it's in 2 places. Then we pop the flags into EDX, and EDX holds the flag values. We AND EDX with bit 8, and this masks off the trap flag. There you go. And at this point, I could just check to see if it's 0, but I might trip one of the little pattern matches. And so they keep going. They rotate left by 24 bits, and it's a 32-bit register, so bit 8 ends up at the carry. So they rotate this thing all the way off, and if the trap flag was set, it's rotated into the carry, which means that now the carry bit holds a copy of the trap flag. It's kind of a little clever thing to do. Then they rotate right, and they rotate right by 1A. So that's 16 plus 10, which is 26. So 26 bits, they shifted over. Now it's in the position of the 0 flag. Okay. Fine. Then they push flags onto the stack. So the whole flags register goes back onto the stack again. There it is. So it's in flags. Now it's on the stack. EDX contains a bunch of zeros, maybe with a 1 in the position of the 0 flag if the trap flag was set. Great. So then I AND the value on the top of the stack to 0 out bit 6. What? What's going on here? Well, I zeroed out the 0 flag. So on top of the stack. So this bit mask with this little B here looks like that in binary. And you see there's ones everywhere except right here where there's a 0 in the position of the 0 flag. So the result is going to be all the original flag settings, but I will have a 0 here no matter what the 0 flag was set to originally. Great. Now I OR this with the value in EDX. So now I started out with this. I OR it with this, and I wind up with whatever the trap flag's value is in the position of the 0 flag. I pop flags off the stack, so it's gone. And now I do a jump 0. Do a jump 0. So I branch on the 0 flag, which is actually a copy of the trap flag. And if I branch, that means the trap flag was originally set way up here at the top, which means I'm probably being sandboxed or debugged, and I can go off and show you pictures of kittens and puppies. And if I don't branch, then I will encrypt your hard drive and demand a ransom. There you go. Pretty simple stuff. But I thought that was kind of fun to look at. And this may seem like a ridiculous thing to do, but this just avoids all the common patterns that a lot of the malware checking stuff looks for. It's just a weird way of shifting it around and playing with the flags, and I thought it was worth going through for a number of reasons. Is all this documented somewhere? How do you find out if you're being sandboxed? Well, there's a tool for that. There's code, and the code can be found on GitHub, and it's called Paranoid Fish. Paranoid Fish is a demonstration tool that goes and checks to see if someone is trying to trace you. And here's what it looks like when you run it. It's like, well, is the debugger present? No. Okay, fine. Forcing V. Look at that. Traced. We're being traced. Look, that bad stuff's happening. So you can use the code in here to copy into your own code to try to figure out if you're being sandboxed or traced or virtualized or whatever thing you may not want to be happening. And all this brings up the question of how does GDB work? And remember, I did promise you at some point I would come back and tell you how GDB works. GDB does not use a trap flag. Well, parts of it might, but for the most part, it's not going to. GDB uses int3. So int3 is unique because there's a special single byte opcode devoted to int3, and it's this one, CC. And obviously, it's an interrupt instruction, so it triggers an interrupt. Since the instruction is a single byte, whenever the interrupt happens, the instruction pointer, RIP, is holding a pointer to the next byte immediately after CC. So if you wanted to know where the interrupt happened, you would just subtract 1 from RIP, and you would know the address of the interrupt. And there you go. So we can peek at the program while being debugged, and maybe we'll find out if GDB is actually using that. So here's some code, quite a bit of code. Most of it just deals with printing stuff. I'm not going to go through all of it, but the basics are, this is your pretty normal setting up for a main. Here's the main, usual stuff and the usual stuff. In between, I print the 16 bytes starting at main, so I load the address of main into RDI. How do I do that? Well, I'm not trying to build a position-independent executable, but I am saying default rel. So this is like rel main, and it's going to create a relocation. And it's going to go ahead and put everything in there. The relocation will get resolved. So once main's address is in RDI, which is the usual first argument, I call px. Px is a little subroutine that prints the 16 bytes in space-separated hexadecimal starting at the address in RDI. So usual stuff and the usual stuff. I put RDI in RSI, so that the stuff I was passing as my first argument goes into the source register. The address of a buffer goes into the destination register. What is that buffer? It's down here. I reserve 49 bytes and call it buffer, and it's in the BSS section, so it's writable. I can't put initialized data here, but I can allocate space. 49 bytes. What is that for? 16 bytes, 2 characters per byte, that's 32, plus a space for each one, so that's 3 times 16, which is 48, plus 1 for a null terminator is 49. There we go. So I do that. I put 16 into RCX. I then go into a loop. I call pbyte. I increment my source index, and I loop back up here, so I just run 16 times, calling pbyte each time. I put a 0 at the location in the buffer pointed to by RDI, which will be the last part of the buffer, so I'll null terminate it. I then load buffer into RDI, which is the first argument for calling puts with respect to PLT. So most of the actual encoding work happens over here. This long stretch of code actually encodes a byte as 3 characters, 2 hexadecimal digits, and a space, and it puts it in the location pointed to by RDI, the destination index. The byte it obtains is from RSI, the source index. Handy to use these registers this way. It just makes sense. So we go and get the contents, we go and get the address of hex, which is this array of hex digits, and we put that in RDX. This is the address of this. If I weren't using an LEF, I used a move, I would go and find the quad word here and stick it in RDX, which is not what I want. I zero out EAX. I then take the byte pointed to by the source index and I put it in AL, which is a single byte. I take AL and I put it in R9B, which is also a single byte. I have 2 copies of that. And that's good because I'm going to mess one of them up. And so I shift right AL by 4, so I drop off the low nibble. I then go and take RDX, which moves the address of hex. I add RAX to it, which is the high nibble, so it's going to be 0 to 15. It's going to pick the right one in here for it, and I put that in AL. I then take the AL byte, and I put it at the location pointed to by the destination index, and I increment the destination index, so I'm pointing to the next slot. It's a good thing I saved this because I'd messed it up, so I move R9B back into AL. I immediately go get the byte pointed to by the source, stick it in AL, do this, do some other stuff here, and repeat the whole process. And really, this is a little bit redundant, but there you go. And it works. So what does this look like when it's run? Let's see if we can find the right place for it. There it is. So let's go ahead and yep, that's the right thing. So let's make it, and it builds just fine. And when we run it, we get the 16 bytes that should be the bytes at the start of our main function. Let's do this. And so let's look for main. There it is. And I don't have the bytes in it. Boo. Let's try 301 bytes. There we go. And so the bytes are 55, 48, 89, E5, etc. And what I got was 55, 48, 89, E5, etc. So, yep, that's working. That's the first 16 bytes at that location. Let's hop into GDB. And let's go ahead and break at main. So we've set a breakpoint at main. If we take a look at main, we'll see here's the stuff that happens. If you remember, typically when you run this and you tell it to break at main, it's going to skip this initial piece and break right here at this LEA. And let's display the bytes, which we can do with R. There we go. Really messy display, but there they are, 55, 48, 89, E5, so on. And so we will stop right here with our breakpoint. So let's go ahead and run it. And we're now at the breakpoint for main. If we disassemble it, here's what we get. Let's continue, and we print out the bytes. And so we print out 55, there's 55, 48, there's 48, 89, there's 89, E5, there it is, 48 CC. Right, there we have it. This is where GDB has inserted our breakpoint. That's how it works. When it does this, it gets a sig break, which causes the program interrupt handler to run and lets GDB trap the program and stop. And that's just how that works. And we could patch the bytes ourselves and put a CC in there and cause the same thing to happen, cause that3 to happen. So that's how your breakpoints work in GDB. And so we did that. Basic idea is you go and you grab the byte, you save it somewhere safe, you put a CC in the place, and then you jump to the address to trigger it. And we can do that because GDB is shoving this little CC into the code. But wait, if you're paying close attention, you might wonder how GDB is able to modify the text section, because the text section should be read-only, right? Maybe it's loading it with write permissions. Well, we can check that. So if we're in GDB and we're looking at CC and we break at main, we run it and it breaks. We can look at the virtual address where we stopped, and we can go and look for the process. So if we were in GDB, break at main, we run, we stop here. This is the virtual address I get for this one, and it's the same one as that one. That's great. And let's go ahead and do a PSF, and there's a bunch of stuff going on. But in particular, we can see this little shell has a GDB running, and it's debugging this file right here. So this is the process associated with that file, and that's its PID. Great. So when we have that, one of the things you can do with the process PID, it's right here, is you can look at what its memory map looks like, and you can use the proc file system to do that. So we would go to proc the PID and maps. In case you're not aware of what's in proc, there's a bunch of stuff in there. And these initial numbered folders, these are processes running on your machine. And this gives you access to information in them. So let's paste our little PID in. And actually, before we do that, let me go ahead and let's see what's in there. There's a whole bunch of different stuff in here. The command lines in here, information about I/O limits and so on, all this good stuff. But in particular, there are the maps. So you see right here, we're going to look at the maps. We're going to do the same thing over here. Just cat them. And there's how memory is allocated in this little piece of code. And we'll go through memory at a later time. We'll talk about what all this stuff is, but some of it should be pretty obvious, right? Here is my program. There's libc, which got mapped in by the mapped in at some point. The dynamic loader arranged for it to get mapped into my address space here. It's really going to load it into memory once, but because of virtualization, it can be mapped in everywhere. We'll talk about these. Here's the dynamic loader. It's in memory too. Here's my stack, and here's my fast syscall area. Maybe we'll talk about that too. All right. Notice here's my code, and I have 1, 2, 3, 4 read-only segments, and this segment right here, which is writable but not executable. This is my BSS, right? This is where I'm writing the bytes, so it has to be writable. But none of the rest of them are writable. And in particular, this guy, which is almost certainly my text section list, that's executable, is not writable. So how is it that GDB is able to write to it, right? We look at it, we find where that address lives. It lives in this space, and it's not writable. So how does GDB change the bytes? It shouldn't be able to. The memory protection system says you can't write to this segment. And GDB is clearly writing to that segment. So I guess all security is out the window. It does it because GDB had the good fortune of being the thing that started our code running, and it gets to use ptrace. And if you go and do a man for ptrace, you will discover that the ptrace system call provides a means by which one process, the tracer, can observe and control the execution of another process, the tracee, and examine and change memory and registers. Wow, that sounds like a really secure thing to have in my system. I'm so glad it's there. It's primarily used to implement breakpoint debugging and system call tracing. A tracee gets to be attached to the tracer. Attachment and subsequent commands are per thread, etc. So there you go. And here's how it does it, right? There's a peak text and a peak data. We can read a word at the address in the tracee's memory, returning the word as a result of the call. Linux does not have a separate text and data address space, so those two requests are equivalent. You can look anywhere you want to. Look anywhere you want to. And you can also modify anything you want to, because again, it doesn't have separate spaces. We didn't know. It just lets you look at and modify anything in the program. So again, very, very secure. The midterm is going to be due on October 5th, 2023. This is a take-home open book, open notes test with no collaboration. It's due at noon on Thursday, November 5th. It is intended to test your understanding of the concepts. Homework is practical, but the midterm is theoretical. The midterm consists of 17 questions. The best 10 answers are counted. That's it. We won't go through the midterm in this recording. We go through it in class.